Hi guys, Ryan here, and today I'm going to show you how to build a search and recommendation engine in Elasticsearch and Ruby on Rails. And before we get started here, I'm going to take you through some of the basics of what a search engine is, how it works, how it differs from a database, and what a recommendation algorithm is, and how that fits into a search engine in general. Then we'll dive into the code and check out an interactive web example that I've got up on GitHub for y'all. So that said, let's get started. So what is a search engine? It's basically a database. Like a database has a schema, which is sort of a plan for the database that tells you what type all the variables are and a list of keys. Well, a search engine has something similar called mappings. And a mapping is essentially a schema. It's type information, sometimes dynamically inferred type information, plus a little bit of extra. It contains also some of the natural language processing ingredients that you might want to tack on for dealing with full text fields. And typically that includes stuff like analyzers, tokenizers, basically the algorithms you want to run on these text fields to break them up into tokens, chunks of words, parts of words, to make things like type-ahead search work, to make things like typo detection work, and internationalization. So that's taken care of. What is an index? Well, a search index is basically a database. Really, I want to keep this simple, so I'll just say it's a place where you store your data, and the name of the index is analogous to the name of the database. So what is indexing? Actually, indexing is the process of storing data into the search engine. Much as a database has a write process, indexing is just the write process into a search engine. And a query is, again, just a question that you can ask the database or search engine that returns records, and it often returns meta information about the query, like how long it took, how many hits there were, that type of thing. Okay, so now you know a search engine, what it is. Let's talk about how to build it. Basically, you need to have a way of getting data into the search engine, and there's two main strategies kind of out there for populating a search engine. Usually the simplest and easiest way to get off the ground is HTTP push, which means anytime there's a change to a model in your web application, that document is modified. You're just sending a new HTTP request to Elasticsearch that says, oh hey, we added a title to this article, or we edited it, or maybe it was deleted, and just notate this in your internal data set as well. So you just stay consistent by a single HTTP request that's fired anytime a change is made and the web application receives it. After a while, you'll see that that has a lot of network overhead, and some of those changes might not necessarily be entirely powerful. For example, a lot of times, if it's a blogging site, for example, people will have several edit passes where they sort of change and look for typos in their text. So you might make a decision. Hey, we don't actually need to save every single change. Maybe every change within 30 seconds is okay, or maybe every change within a couple minutes is okay. If that's your sort of application, you may find you can do a lot with JDBC pull, which is just you have a database connection that's made directly with the database, and data is drained into Elasticsearch asynchronously over time. And I've actually built an open source library for doing this, which I hope to be releasing publicly on GitHub soon, but that remains to be seen. And I know there's a few out there already too in the community, so there's plenty of stuff out there if you're looking to do one of those pull-based ETLs. So here today, just to get off the ground, we're going to use push behavior, which is basically, again, anytime the model is saved or destroyed, it calls a callback. Well, you can wire that up by hand and use a low-level client like the official Elasticsearch client, or you can actually do what we're going to use today, which is just use the Elasticsearch model gem, which kind of sets up a lot of these callbacks for you and just streamlines the whole development process. So that said, we know how to get data into the search engine. We know how to install it in the box. Brew install Elasticsearch. So then how do I actually construct a search, and how do I make a web application that has a search box? Well, at the high level, here's a simple architecture. Basically, you've got a web form, lives in the view, and when users click buttons or boxes or type text, it's just changing URL parameters. It's saying, and the search text equals, and then whatever they typed in the search box. Or maybe it says, and checkbox status for, show only results in Kansas City. equals true. And you can construct an arbitrary web form that sends arbitrary parameters. And then all you do, with most web forms, is you just pass those parameters to the index action of some controller, and the controller basically just makes a single call to a search model. The search model is going to contain basically all of the business logic for constructing search query JSON. Elasticsearch has an HTTP API. It accepts JSON objects, which are just lists of, hey, we want to do a query. These fields have to have these values. Look for text that matches these tokens. It's well documented. It's up on the web. There's seminars in it. There's meetups about it. So a really nice and comprehensive JSON API. So all you need to do is build a simple model that can construct a few relevant search queries to your business application and fill in the right blanks with sanitized parameters from your controller. And then once you've got, to recap, you've got parameters that are sent from the view, just goes to the controller. The controller doesn't do much except zing them off to a model. The model just builds a little JSON blob and fires that to Elasticsearch. And you just take the results of that search query, send them back to the controller, and fill in an instance variable that says, hey, the set of documents you wanted, here it is. That's it. You just render that in the view and you're done. So it's a really simple architecture and pretty standard stuff for most web application developers. I just want to say that these days, people are doing a lot of this AJAX behavior for search. So they're looking for, key up events in JavaScript and firing off search events pretty quickly, based on only partial text entries. And the idea there is you can do some really cool stuff for the user experience, right? You can do type ahead search, where you sort of see the first prefix of what they're going to type and then guess what they're going to type next. Like you can actually fire off a different type of search and render a different type of search result in your view, like for example a little pop-down menu that has suggested searches or typo detection, that type of thing. So there's a lot of really interesting stuff you can do with sort of query understanding and searches that are run before you actually fire the big one, which is when they click the button or click on something in a type ahead box. And that's when they would have you would ideally have the most clear idea of what the user is looking for. So user experience and application architecture aside, if you've gotten this far, you essentially have a functional web app with a search box. So at this point, your goal is to take it to the next level. How can you get more clicks? How can you show more relevant stuff to users? All the stuff that web businesses tend to care about. So there's essentially two major paradigms for training search models out there on the web today. The first one is sort of the log data approach, where you simply look at all the documents that users saw as a result of firing search queries and all the ones that they clicked on. You look at and that's the dichotomy. Logistic regressions or classifiers in general for machine learning are just designed to detect dichotomies in data. So you would simply mark all the records that were shown and clicked on as outcome 1, and all the records that were shown and not clicked on as outcome 0. You would feed it some features or ingredients, predictive variables that might prove to be useful in recommendation algorithms, such as things like, well, how closely am I connected to the author of this post on some social measure? You might include things like time decay, of how old is the post. You might include measures of trendiness or relevance. And of course, you can include the features that the search engine keeps internally, such as how relevant was the text match. In fact, you can do several of these types of algorithms as well and ensemble the results. So that's sort of one approach, which is passive data collection and quantitative iteration. There's a second approach, which is what Google does, or at least used to do. And this is where you have sort of a battalion of expert users or volunteers who runs a few search queries. They run your most popular search queries usually. You can actually look at your log data, see what the most popular search queries are, and then have a prioritized list of iterables for your volunteers to tackle. And the volunteers will order the set of items returned by the search engine for each search query. Perhaps they'll order the first few pages of these results, and they'll do it by hand. In this case, you have a sort of paired comparison outcome. So you change the target and you change the features. You essentially say, here my dichotomy is going to be the difference in ranking between these two objects. So your targets will become, for any two items, is the first item greater than the second one, and then the coefficients and the features will just be the difference of the features that you are going to include on the sort of the log data approach. If you do this and you collect enough data, again, you can train a logistic regression which will give you values for your coefficients, which you can then plug into your model. Just as a quick note, oftentimes it's a little risky to make huge changes in these lookups all at once. So usually there's a period where obviously you'll A/B test new algorithms, expose them to smaller subsets of users. And it's also good in terms of statistics to sort of keep the learning rate small. So if you have a new model that is significantly different from the old one, oftentimes rather than immediately rolling the result that comes out of your initial statistical result to production, you would actually go ahead and take a measured approach. I call it like product manager gradient descent, where you sort of take the difference between what you have, what the math says you should have, and step it by a small degree of iteration rather than going all the way at once. And this keeps you from making over-optimizations and big mistakes, and it keeps the result set fairly consistent with the old one, which is oftentimes appreciated by users. Giant changes can be beneficial, but they can also be jarring. And so usually it's best to kind of step into new models a little bit at a time rather than immediately rolling something completely breaking tradition with what you had before. And again, this differs by application area, so experiment with this on your own. Anyway, so you've got your coefficients from one or both of these learning approaches. What do you do next? Just simply put the coefficients in the search query. These days search engines allow you to score pretty much arbitrary regression equations. So you should be able to construct a query in your search model that is highly representative, if not exactly the same as the regression equation that you've learned. So that said, let's go through an implementation. I'll take you guys through the Rails code right now to build a quick little example application with one of these so you can get up and running. Okay, before we start looking at code, I wanted to show you guys the finished product and first give a quick shout out to the Elasticsearch Rails gem, which I'm using throughout this application. So the Elasticsearch Rails gem is pretty cool. It gives a higher level API to Elasticsearch for Ruby on Rails applications than the official Elasticsearch Ruby client, and it offers a few nice things to sort of get you up and running and experimenting with this stuff quickly and easily, such as active record callbacks automatically wired up for you, and convenient result parsers for search responses. It offers some rake tasks for seeding your database, as well as a nice example template generating function, which I pretty much shamelessly ripped off in order to do my own example application for this talk. Pretty much I'm using their verbatim, I think it's template number 2, template name pretty, for an example search application with a few columns added. I threw in a trendiness score, which is randomly generated. I wrote my own seed database file, which creates about 100 fake documents and randomly fills in prices and trendiness for every single one of them. And what the goal here is I want to show you guys essentially a working implementation of a search app that's capable of doing searches and capable of doing recommendations. So it might not look like it, but when I refresh this page here, I've got it wired up so that it's running a recommendation algorithm in the background, and it's printing the score directly into this score box. So you can see it's ordering the search results by score with the highest scores up top, where that score is essentially going to be the score of any arbitrary regression model that I can dream up and then translate into Elasticsearch query code. The Elasticsearch query API again, is very expressive and allows a wide range of this stuff in here. They've made a big step forward by adding the functional scoring API in the Elasticsearch 1.0 release, and it's pretty great. And then second, it's also capable of your typical search stuff where I can type in a number or text, and I see the relevant articles as well. So that said, let's dive into the architecture. Okay, so let's look at the code base, and I'm going to explain the code base exactly as I did in the presentation, which is a round trip between the views, where the user is asked for input and via a search form, into the controllers, where the saved user input from the search form, saved via URL parameters, are passed to a search model that fills out a search query and sends the results back to the controller as an instance variable, and then the controller just renders the results of the search query back into the view. So a simple web form round trip here. And let's start looking at the files. So here in the views, in the index view, which is where all the action happens on this app, you can see the very first item on the page is a simple web form, which has a single text field filling in the parameter Q with whatever they type into the box. You can also imagine a web form with a lot more buttons and fancy parameters being collected. This is a demo app, so here we're just doing a pretty simple collection of one parameter via a text input field. That user input is just getting sent straight back to the articles controller, and in this case it's going to the search route. Elasticsearch Rails, that gem actually provides a convenience method called article.search. It's just a simple method on the object that runs a search with parameters that you can provide yourself. And since I didn't really have any reason to make a super special search model, I was kind of focused on building a recommendation algorithm and showing you guys how to score regression models in Elasticsearch. I just left this one verbatim. Here in the recommendation action, you can see a call to a model that I've created that we'll go through in a second, rec algorithm.trendy and pricey. And I have a rec algorithm model or class, I guess. That is, it's just a container for like 4 or 5, actually in this case just 2, but n number of pre-built Elasticsearch queries that are representative of different recommendation ideas, ways to choose items to recommend to your user. And just a quick note on the style of this controller. It's really nicely encapsulated in that there's a separate action for every different algorithm that we want to run. There's no overlap between search and recommendation here, and there's not really any messy parameter checking logic that happens in the controller that sometimes you see blowing up the code base, in big search projects. So it's cool that we've got a nicely segregated code base here. Okay, so let's look at the the recommendation model and see what I cooked up for you guys today. And here I just wrote in a couple functional scoring queries. While this looks like a big chunk of JSON, this is really straight out of an example directly on the Elasticsearch webpage, and their docs are very user-friendly. So what I wanted to show off here is essentially use of the function score API to score an arbitrary regression function, which I've provided here. So essentially this is the only component of this document that I've actually modified myself. And all I did is I took the document score, from whatever the search match was. In this case, the search match is match all, so it doesn't matter. But you could put a filter search here, or any number of other ideas. And I've just added a simple regression to the end, where I'm taking coefficients, 2 and 0.5 times variables, the trendiness value and the price value. And then I'm adding them up together. And what's cool about this is actually the functional scoring API allows you to have several of these little scores. You can run them over subsets of the data. It's possible to put a filter within each of these functions. So it's just a really nice extensible framework where you can have really complicated mathematical expressions being evaluated against your code base live in milliseconds. So it's a pretty cool API, and I can't wait to see what people start to do with it as it becomes more widely discovered. Um, anyway, so once we've constructed our search query here, we just go back to the controller, and we fill in this articles instance variable with the result set that comes out of running our query. And then those instance variables get rendered back into the view down here at articles each due article. So I've got this up on GitHub, and I'll show you the steps below in text. Really, there's not much more to it than what I've just described. I did create this seeds script where I'm randomly generating a bunch of fake articles. And really the only other secret sauce left is how to run a regression using something like R. Okay, so since we're a Ruby on Rails crowd, I'm going to quickly step through an example logistic regression, just so you guys can get a sense of once you've started collecting data from your web application, the impression and click-through history, or perhaps your community of experts ranking results. How can you then go and build your own improvements on your search algorithm and start getting those better click-throughs and those really nice custom domain models that'll really help your web company take its site experience to the next level. So I didn't actually have access to any publicly available click-through data to build a model directly in the same domain. So what I'm kind of falling back to here is I'm just going to teach you the process of building a logistic regression model. And I'm going to keep it pretty quick and dirty and just step through an established example page that you guys can all run on your own time and access just out on the web. And the one I settled on is this one by the Institute for Digital Research and Education at UCLA, and we're just going to follow the steps verbatim here. So this particular example requires some libraries, some little code packages to be included in the file. I've included them up here, and actually, if you're lacking these on your system, go ahead and run install.packages on the name of the package, and that will install it. If you already have it, it'll try and update. And I also wanted to say the statistical language that I'm using here in the program I'm using is RStudio. RStudio is just a sort of an IDE, an integrated development environment for the statistical programming language R. There are many statistical programming languages out there. There's R, there's Julia, Python often is used, and if you're at a large financial institution on the East Coast, you're probably using SAS. All of these languages have their particular strengths and weaknesses, but R is free, it's open source, and it's been around for a long time, so there's a ton of documentation and examples out there. So for this particular use case, I'm just going to quickly step through an example in R, and if you have other preferences, feel free to explore those on your own. So the first step in R is to load data from a file somewhere or a database. In this case, it's a file that happens to be stored at on a web server. Read that into memory into an object called a data frame, and a data frame is just it's a nice sort of like rectangular data store that contains a notion of missing data, allows row and column access, and some convenience functions. For example, the head method, which will give you the first few records in the data frame, which you can visually inspect to see if you've made an import error and your data is stored, incorrectly, as well as the summary method, which will give you quantiles. Quantiles are well, if you're familiar with the concept of a median, which is the idea that 50% of the data lies above and below the median, the quantiles are sort of other percentage cuts in the data. So the first quantile is where 25% of the data lies below and 75% above, et cetera, et cetera. And we've got that broken down for every variable in the data frame. So let's step back and talk about what this data represents. Here, the dichotomy that our regression is trying to predict is whether someone got admitted to a particular, I think it's an academic program, And the predictive variables that we have access to in order to make this decision are their scores on a standardized test called the GRE. We have their grade point average. And then we have rank, which I think is, it's only 1, 2, 3, or 4, which I believe is placement in a class quantile or something like that. Um, and I'm sure if we actually read the example, we'd have a better idea of what that rank variable actually meant. But here I'm just trying to drive to results. So that said, we're going to skip a couple of these. Here they're running the standard deviation algorithm on my data and checking out what the standard deviation of each of the variables is. And then they're doing some cross tabulations, which are basically pivot tables, simply looking at how many people were admitted by each class rank variable. So just data exploration, getting a physical feel for how our data looks, how it's performing. And this is the first step of any statistical analysis, is sort of diving in and looking at the data, seeing if there are problems with it, because you can't build a common expression in programming, I guess, is garbage in, garbage out. And that definitely applies to mathematical programming as well. You have to make sure that your features you're passing in are valid, or else you have a high probability of building a algorithm that just doesn't really add any value. So here they decided to perform a little bit of a statistical transformation. They decided that the rank variable didn't seem to be linearly correlated with admittance. And so what I'm going to do is run the same code they did that just says, okay, treat the rank value of 1 as unrelated to 2, 3, and 4. So there's not necessarily an implied linear correlation. This is just a feature transformation, and you can sort of figure these out on your own, looking at the data and playing with it. At this point, we've sort of finished our data exploration. We've landed on a set of features. We're going to use the GRE score, the GPA, and the factor version of rank. And now they're ready to do their model selection. So they're going to start fitting logistic regressions and ultimately land on one as better than the others, which will then produce the coefficients that will ultimately be used to make business decisions on. And if this was page tracking data and a search problem, then we would literally just be taking the coefficients that we've determined by performing this regression, and we would just plop them right back into our search model, our recommendation model, and start serving them to users and experimenting online and seeing how they affect the site experience, both qualitatively and quantitatively. I mean, one of the most important things in web is you always want to have a really tight loop between actually looking at stuff, having people look at stuff, telling you if it's making sense or not, because it's pretty easy to over-optimize and take too big of a jump. But anyway, that's all kind of beside itself. So here we fit a regression by running the GLM function. This is the general linear model function. All we said is, hey, it's a logistic regression, and here's the model specification, and run it on our my data set. And as you can see, we can go ahead and get the fit statistics that will tell us how good the model was on this particular set of data. Now this is what's called a training set. Usually when you're actually building production models, you would reserve some set of the data, and you would score the regression against the reserved set, which is called the validation set. The idea is the training algorithm has never seen data from the validation set, so that results on the validation set are kind of a clear indicator of how your model might do on new data as opposed to data that it's already seen before. So that's just something to keep in mind. They didn't really do it here. So when you're looking at logistic regression scoring output, you definitely want to keep your eyes on these significance codes. You want to make sure that most or all of your coefficients are found to be statistically significant at, I'll just arbitrarily say the 0.01% significance level. If they're not, your model specification is called invalid, and you have all kinds of statistical problems with it, where essentially because some of the variables don't actually seem to exhibit good correlation with the output, you can have counterfactual results being suggested. So the idea is in regressions you tend to want to build valid models, and one of the signs of a valid model is significant coefficients. Another one is values of coefficients lining up with what you expect in your business situation. So for example, if rank is class rank and rank 1 is the best rank and rank 4 is the worst, here we can see a clear linear progression from the score of 0 for rank 1 to increasingly negative effects the worse your placement in the class was. We can see a positive relationship between better GRE scores means you get a better probability of admittance, and better GPA, meaning a better probability of admittance and being very strongly correlated. I'm sorry, not strongly correlated, but being significant and having a large coefficient. So anyway, the next step is you would sort of look at your goodness of fit metrics and graph your sort of validation results. I don't know how deep into this I want to get, other than I'll just pause here and say ultimately you'll have several candidate models. The idea is you want to choose the models that have the strongest performance on the validation set. You can measure performance by using what's called a goodness of fit metric. There's a few nice ones in industry. A lot of people use what's called rank correlation statistics. For example, stuff like Kendall's tau or Summers D. These are statistics that tell you for a couple different rankings of, for example, search items, how closely they are related to each other, how closely correlated they are. But you can also use some simpler ideas or ideas you may have more familiarity with, such as the R-squared, which is just the squared correlation between prediction and outcome on your data set. Or something like, and I believe, I never quite learned how to pronounce this correctly, it's I believe the Akaike information criterion, which is down here when you just run the standard summary output, and lower is better. So if you have a set of models, you want to go for lower there. And then of course you want to maximize your goodness, or you want to get a strong goodness measure for your whatever model you choose. You also want to make sure the model is valid. Some quick tests to make sure the model is valid is, as we discussed, significant variables, coefficients, estimates that make sense, that are in the right direction. And finally, you want to make sure that none of your predictors are really highly correlated with each other. For example, yeah, just the idea is if you have two really highly correlated predictors, you have all kinds of problems with what's called multicollinearity, where your coefficients blow up and your estimates become meaningless. And so a quick way to test for that is to just compute a statistic called the variance inflation factor. And there's a little package that will just automatically do it in R, and that will actually run several regressions. It'll just regress every single predictor variable you have on each other and see if there's any linear combination of the other predictors that strongly predicts one of the other ones. And if there is, it'll have a really high VIF score, which basically means, hey, you need to pop this variable out of the model. Anyway, that said, I believe now we've covered giving you guys the tools to build awesome statistical models, populate them into a web framework, and actually serve results to users. So once you start tracking data on your web app, you should be totally set to start really taking your search and recommendation platform to the next level and beginning to have a quantitative plan for improvement. So that said, I'm going to close the video here. Thanks for checking it out, guys, and ping me if you have any questions via, I guess, Twitter. Yeah, Twitter would probably be the best mechanism, and thanks again.